Test, 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 test. Yeah, okay, cool. Sorry for the glitch. The issue. A little tension here as the little baby is about to come, and then yeah. Hearing someone shout outside of the room doesn't always help. Now back in there. Yeah, what about this? So Peter, and I don't know if I don't know if that's like showing up in the same chat or not. So the biggest thing for us was that before there was almost zero discoverability, but now there's a new category for everything programming and game development, writing. So yeah, I don't know. I guess I might. Yeah, so I'm streaming in science and technology. And the thing is, I'm doing kind of like really a mixture of programming and not programming, right? So I'm not so sure it always fits. I guess one doesn't have to always stream in the same category. So yeah, I'm pretty new to Twitch, to be honest. Um, and I don't know. But yeah, thanks for letting me know. So that is actually, it's a good to know. I mean, Twitch. So let's see if I cannot hear myself. 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 Let's see if I can. Okay, software and game development. Yeah, definitely. I mean, why not? That is cool, actually. Yeah, I'm doing kind of a bit of everything, so we'll see. Um, right now, I'm still in science and technology, I guess. Yeah, it's I'm kind of like trying to still find my way through the Twitch thing. So I really a lot of times I will just kind of read things, but yeah, I do like it's like 50-50 coding and reading. So I don't know. We'll probably choose the category based on what I would be planning to do. Um, I don't know if I can change it midstream. Can I do that? Development. Yeah, we'll see. I'll play with these later. Well, definitely for the next stream. Um, Now back to the thing, and I don't know how far we'll get today because, to be honest, there's not much time, and I should probably have planned it in another way. But I'm trying to find a way. I'm trying to find a way to do exercises and kind of like build or kind of go through path integral and Schrodinger equation kind of stuff programmatically. Um, and the reason just being all right. Yeah, exactly. So at the end of the day, that's what I'm trying to do. It's really kind of live learning, live researching, live coding. So cool. Thanks for letting me know. Thank you. Um, yeah. So how are we gonna do these? I mean, what is the goal? So the goal is so I can kind of go through things like these, and the goal is so I can go through things like these and kind of validate what I'm trying to do either by hand or yeah. Or I guess at the same time learn, right? So we'll see. But now the thing is, what do I need? Like here, there's no like if I go to the Qt page, so there's some tutorials. This time-dependent evolution simulation. So there is actually evolution simulations, right? But it's like it almost feels like Qtip is really focused in automating that away, so in actually getting to the solutions, right? Um, so that's why the whole thing with the time evolution, it's like qubit dynamics, Flockett formalism, stochastic, blah 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 blah. How does this even feed? I mean, qubit integrate. I have absolutely no idea what is it. What is these? So these are different solvers. In a block sphere. So the James Covey model is the simplest possible model for quantum mechanical light-matter interaction. Describes a single two-level atom interacting with a single electromagnetic cavity mode. So this is the Hamiltonian, and so what these. So this is just really specific to that Hamiltonian, right? So you build a Hamiltonian like these. Then you kind of just like time evolve the thing. Hmm. Mm, Hermitian operators, custom algorithms, multiprocessing, can express time independence analytically, or need to construct the function from a data set. No problem. Kit allows passing interpolation functions. So that's more like advanced stuff. Built-in solvers for dynamical simulations. Yeah. Okay. So I think QTIP is not, because QTIP is, as I said, seems to be more solution oriented, and I just want something that helps me automate the equations, or not automate, but like, yeah, kind of do the help me do these, right? Help me kind of solve some of these things. Help me kind of. So essentially, I think I'll have to go with SymPy, but I don't even know where to start, right? Because SymPy does actually have some quantum mechanics stuff, but it's really I think you should be able to do most of these things just in a standard, just using the standard SymPy. That's the thing, right? Like I really it would be cool to kind of get familiar with the SymPy stuff in terms of being able to write these equations smoothly. I don't even know where to start. I guess I'll just have to go through one very specific um, example. I just like SymPy, so solving the path integral with SymPy or just Python. Like, what happens if I search for these? What are line integrals? Oh, so these are path integrals. Well, a line integral is an integral where the function to be integrated is evaluated along a curve. The terms path integral are also used. What is the difference then? Line integral. Because that might essentially help me understand a bit more the whole thing, right? Because I really didn't know that actually has a specific type of definition that is actually not the same like the integral. So an integral assigns numbers to functions in a way that describes displacement, area, volume, and other concepts that arise by combining infinitesimal data. The process of finding integrals is called integration. But the line integral is an integral where the function to be integrated is evaluated along a curve. Complex plane. So the function to be integrated may be a scalar field or a vector field. The value of the line integral is the sum of values of the field at all points in the curve, weighted by some scalar function. Okay, so this is actually a different definition of an integral, as in like it's not the area, but it's the value of the it's the sum of values of the field at all points in the curve, weighted by some scalar function on the curve, commonly an arc length or a vector field, a scalar product, a vector field, differential vector. This weighting distinguishes the line integral from simple integrals defined on intervals. Yeah, no, okay, but it is in a way the same concept, is it? Because you sum all the values and that gives you the area, because it is for infinitesimal. Okay, but there is some kind of weighting. That is what makes it different. Okay, that's already interesting. So the contribution to propagator from a particular trajectory is these there are possible conditions of the propagator, but with a phase related to the summing it all possible trajectories, we arrive at the propagator, the normalization constant, blah blah blah. Glacial action, yeah, but where is the so you have the sum of all trajectories, and that is, yeah, okay, so that is why this is called a line. So this is the weighting factor, I guess, A of t. So what is these? Scython. What? Okay, so, but I've seen these here. So I've seen, if I search for, so that would be a good starting point. Line integrals. I thought I saw that. Sim pi. I didn't think that was the same thing. Vector integrals. Okay, so these are, I think, curve path. Yeah, okay, so this is it. So to integrate a scalar or a vector field over a region, we have to first define a region. Okay, so that is actually it. Calculation of flux. Cool. So there's the tooling for these in here as well. So you can define a region and volume. Mass of a body. But there's no actual integration example. Oh yeah, the vector integrate function is used to integrate scalar vector fields over any type of region. It automatically determines the type of integration, line, surface, or volume. Oh, so there's... Oh, okay. Surface integral. So there are things like, what is these? Surface integral. So in mathematics, the surface integral is a generalization of multiple integrals to integration over surfaces. It can be thought of as the double integral analog of the line integral. Given a surface, one may integrate a scalar field that is a function of position, which returns a scalar as a value over the surface of a vector field. Okay, so in the line, so the line or the path integral would just be you have that field, and then you're just integrating a path. Okay. That's cool because now it starts to kind of fall into place a bit more, right? It's just an integral. If you're just take a function, right? An integral is what it is. You have like a function that's got like a two-dimensional function, and then you've in x and y, and so the integral is you're counting that you're adding these infinitesimal or the values in this the errors in this infinitesimal sort of deltas, right? And that gives you the integral. Uh, yeah. And when you're and so the path integral is just saying you have a so you have like say a two-dimensional plane, just as an example. And what you want to do is you don't want to integrate the whole thing. You just want to integrate the values across the path. So this is just a way to formally say I want to add those little, I just want to count something along this path. Is it, the sum of the values, and then okay, so it starts making sense. So there is this thing here, so you can actually do that. And then the vector integrate will actually do that. So, but you need to give it the region. So you need to define the region, and then perimeter, surface area, and volume. So that would be if you just want to kind of calculate like of the perimeter of a circle, if you want to do sort of the Yeah, and vector integrate, and then you have the integration. Cool. But you can also integrate over a volume or integrate over a surface. Okay. Now we need this to work. So at the end, this is a complex vector field, is it? Yeah. Is it? Yes, because you have you have um, you have a state vector, don't you? You have a state at any point in your plane. But we also have an action. Hmm. So instead is for probability finding the particle at these locations, which is related to wave functions. So we have the wave function at this point in space and time. We have the wave function. So it's what's more, it's wave functions, right? So it's not just states. It's yeah. I mean, it's the wave function, right? So yeah, that is actually a state, right? It could be a superposition. The total transition probability amplitude, you can do this by summing the amplitudes of the particle having taken any individual path. If the quantity can be calculated in the method suggested, the evolution of the state can be determined by considering contributions from all possible future states, and the problem is solved. Below, the kits are eigenstates of the position operator and such integration on a linear basis. Below, the kits are eigenstates of the position operator such that the integration over all x spans the entire basis. So the wave function at a given point in time is the sort of the integration for an infinitesimal change in x, that will be x prime, right? So mechanics in this paper will present the method used by Feynman. Though it is pedagogically backwards, we'll then demonstrate the use of the method before showing the equivalent social picture. So here you have the propagator. It's still, I'm still feeling a bit uncomfortable with just the whole concept of the space-time points and then the probability transition. Like, how would it be that there's a zero probability transition, for example, between two space-time points? So can relabel the first time. The propagator above, along with the initial state get, fully describes the evolution of a system over time. It is also customary, as it is done in. So what you want to do with the path integral is you want to reconstruct this propagator. So you consider all the possible trajectories of a particle moving through a time-independent potential with endpoints fixed. So there's an infinite continuum of such trajectories, each with classical action. So there's a classical action associated to to the trajectory. Trajectories, we are at the propagator. Yeah, okay, but you need to have that, right? So we know the action stuff. Let's go through the free particle stuff again. So for correctness, we use the method above. The propagator for the simplest of systems, a particle moving in free space along one dimension. In this case, we'll actually evaluate the integral given above, so all the possible paths, although okay, so there's ways you want to avoid to do this, but that's just the simplest example. So this is trajectory from xata to xbtb. We discretize the trajectory by dividing into chunks. But it's funny, so chunks of time, right? Because we're only thinking about time evolution. So we're thinking about no, but it's going to have to be so we discretize the trajectory by dividing into chunks of time. So n chunks of time, such that the intermediate points are yeah, okay. So we of course we don't know what happens with these, right? So we don't know if maybe it just stays stationary in x1. So x1 and xn minus 1 might be the same. We don't know. We're just split that in chunks, and so we do this with the hope that in the limit when n approaches infinity, the model is just a continuous path. So there's no potential. So the action depends only on the velocity, which between ti and ti plus 1 is constant velocity. So the action in one of the specific chunks why is the integral in this case? Of the kinetic energy, right? That's the integral of the kinetic energy. So to describe every path from x0, t0 to xn, tn, we simply vary each intermediate point at each ti over the entire domain. I think this is omitting the sum, by the way. But we're calculating the action. Okay, so what you want to do is calculate the action of every path. By adding the action of every single small step in each path. And then you want to add all over the trajectories of these. So this is still not fully clear. But to describe every path, we simply vary each intermediate point xi at each Ti over time. And so here you get basically the over each path. So here, so each of these things, like each of these integrals is just one path, right? So you do this for all the paths. So here they just then realize there's a pattern, and there you go, and off you go, right? So, and then the propagator, so the propagator is essentially, it's got this expression that then it just depends on x0 and x, and then in the mass of the particle, blah blah blah, just because it's a free particle. So we can have like this kind of neat expression here. But essentially, what we're doing is we're just taking every path, we're splitting it in chunks, calculating the action of each path, and then doing a sum over all the paths, and that kind of gives you that yeah, that I think that all makes more or less sense. Maybe this part is the one that I still want to dig into a little bit. Why we're doing an integral between Ti and Ti plus 1 to calculate the action. And like that equivalence, how do we go from here to here? Oh, okay. So I think there's a big step in here. So I think I could even do this by hand, I think, because I think what it's doing is just doing that classical rule of like, you know, the integrated version of these evaluated at this point minus the one evaluated at Ti. It's just that this part here is factored out. Yeah, of course. Okay. Yeah. Not so sure about these though. About what's between the parentheses in here. But okay. So that is the integration of that. But that's the first derivative of this square. So I'm not so sure why would that be like that, like xi plus 1 minus xi. That is a bit confusing. But yeah, that's okay. So that's how you define the action. Because the thing here is the action is, I don't know why you do why do you do the integral though. The action, why isn't it just the kinetic energy? Why don't we just use these? Because I thought those were small chunks anyway, right? Or not? Hmm. Anyway, that should, and then the equivalence of the Schrodinger picture and the harmonic oscillator. But here now they start messing up with Lagrangians. So okay, so I'll aim at doing this one next time. But then I need to know what the heck is happening here with the Lagrangians. So the harmonic oscillator. So you have the potential, and then we're perturbed in a slightly different manner. So the classical path and its velocity respectively, we can represent any other path as deviation from this one. But what is the classical path in the first place? So here they define all the other, instead of just going through all the paths, you just define this the classical path, and then define that there's, I guess, infinite many paths that like are somewhat around this path, and then rewrite the Lagrangian for generic path in a way that isolates the classical Lagrangian. So how can we do Lagrangians in SymPy? We know we could do line integrals. So yeah, okay, no, that's not, that's the Lagrangian as in the action thingy. And what we want to do is the following form. I see the integration is really used loosely as like sum in here, right? But this is just a Lagrangian. What is these? Like what is these Lagrangian? What does it mean? Like is it Wikipedia? I Lagrangian. So I think that is something to do with the constraints, right? Like path Lagrangian. Lagrangian system be apparent in this way that is both a function called Lagrangian. No, but that is potential minus kinetic. So they actually might be doing these here as well. Yeah, actually they're doing that. Yeah. So that is actually the Lagrangian. I see. So this, I think this is because I think this is kinetic energy and somewhere potential energy. I think. Because I see mass and velocity squared and blah blah blah. Okay, so I need to go through these, I guess. But that is apparently doable. So the first term is just Lagrange for the classical trajectory. The second is zero by the all Lagrange equation since the stationary path. Since on the stationary path, this term must be zero for any well-behaved deviation y. Oh God. I like to know more about this stuff. It's complicated. There's just a lot of things to look at. A lot of little details. The order Lagrange equations is simple second order ordinary differential equations whose solutions are stationary points of a given action functional. Okay, we'll definitely need to dig into this. I think that we should just try with Simpai. It seems to be a good candidate. And 20 years later, the third term is the Lagrangian for the deviation. The action is separable in the sense that the propagator has the following form. Why do we start by defining a Lagrangian, though? This is what I don't understand. Why do we even use a Lagrangian? Um, that is complicated. Euclidean path integrals. Okay, that would be. I'll, yeah, I'll finish now. I just don't have the head for this today. But yeah, gotta keep digging into these, and I almost feel like I really haven't actually done anything productive other than like kind of taking a look at Simpai. But okay, we'll get going. I just gotta dig into these a bit more. So I just gotta have to. I think I understand that generic approach, but that's okay. I get it. That's not what you want to do, and you won't always find this kind of patterns. Um, Here you're doing. So it's the harmonic oscillator. That is just the. Based path visualizations. So how do you derive that? So you do that like that's what I don't fully understand why you do this with the Lagrangian. Um, but okay, gotta think about these a bit more. And yeah, I think I'll really get coding next time. Um, Try to do that in a notebook. See if I can kind of manage these type of expressions in a way that makes any kind of sense to me. And working with Lagrangians. I definitely probably have to do. You know what? I think I have to do a Lagrangian style. I think I have to dig into the Lagrangian thing. It seems really that it's all over the place. Anyway, and I should just be a bit more familiar with these. Um, yeah. Anyway, gotta reset a little bit my brain today.